Planck's famous formula tells us that the frequency of a light particle is proportional to its energy. So maybe energy also determines the frequency of our mass particle. The energy is equal to the mass times the speed of light squared, which tells us that the frequency of a particle is proportional to its mass. But what if the particle gets moving? For what happens to a clock that is moving? It slows down, right? You know it because of relativistic time dilation. So the inner frequency of a particle then must decrease. On the other hand, if a particle is moving, it has kinetic energy. So it should have more energy than a stationary particle. So it would follow that the frequency ought to increase. A contradiction. Our beautiful mass-frequency relation seems to break down immediately as we set the particle moving. And the solution arises from the same source which created the paradox, the theory of special relativity. For our picture is wrong, and we have forgotten about a crucial effect in relativity. Let us simplify the setting to get a clear understanding of the consequences. These pointers represent clocks. In this frame, they are synchronized. However, when we accelerate, Einstein says that the clocks in front of us skip ahead in time. In this moving frame, then, the clocks are no longer in sync, and in fact seem to create waves with their phases. Let us set the ground plane in oscillation too. Again, as we move relative to the ground, both the clocks and the ground go out of sync, thereby creating phase waves in the moving frame. Going back to the localized particle, we now understand that there will be a very important additional effect in the picture. The moving wave packet acquires ripples. It is these ripples that will salvage our broken mass-frequency relationship. And it's the wavelength of these ripples which will be associated with the momentum of the particles.